Welcome to another podcast. This episode, we're going to be taking a look at one of the last things of the semester, and that is what are unit step and impulse responses, and how do they tie into convolution. I'm going to illustrate this with an example. So suppose you were asked to look at the function, or the differential equation, y double prime plus 6y prime plus 8y equal f of t, where I'm not specifying the forcing function, but we're going to have rest initial conditions. So y of 0 equal y prime of 0 equals 0. Now, under this setting, I want to use the Laplace transform to solve this particular differential equation. And I know you might be sitting there thinking, but we don't have a right-hand side. Well, it turns out that that's unimportant when it comes to solving using the transform. We can actually come up with a solution via an integral formula that would give us the solution for any right-hand side. So let's do that. I'm going to start by taking the Laplace transform of both sides. The Laplace transform of little f would be capital F. And on the right-hand side, we have the Laplace transform of the second derivative. Plus 6 times the Laplace transform of the first derivative, plus 8 times the Laplace transform of y, which is just capital Y. So one of the beauties of working with rest initial conditions is you can see both y of 0 and y prime of 0 is 0, so this term, and this term will all be 0. And what that ultimately results in is that we can pull out the characteristic polynomial s squared plus 6s plus s that's multiplied by the transform variable y of s, and that's the only thing that's left on the left-hand side. So that when it comes time to solve for y of s, the transform variable is simply the transform of the forcing function divided by the characteristic polynomial. Now, if you've watched the Duhamel's principle video, you'll have seen that this is essentially a convolution of the forcing function. That this is essentially a convolution of the inverse of the forcing function's transform convolved with the inverse transform of 1 over s squared plus 6s plus 8. And in that video, it talks about how this function is something called the weight function. Well, if we just continue this problem out, we know that the inverse transform of y of s would be little y of t, and based on what we have here, this would just be f of t convolved with whatever the inverse transform of this is. Now, it turns out that this factors, so this is actually, if you look at this particular thing, this is actually 1 over s plus 4 s plus 2. So we can see that that would involve an e to the minus 4t and an e to the minus 2t. And if you do partial fractions there and separate them out, what you'll end up with is minus 1/2 e to the minus 4t plus 1/2 e to the minus 2t. So this is our solution, and we tend to want to write this in integral form. So this is called the convolution product solution. And that convolution product here would be the integral from 0 to t of f of t minus u times this function 1/2 e to the minus 4u plus 1/2 e to the minus 2u du. So this is our first attempt at a solution to this problem. It is a solution which gives me any starting function f of t. So f of t is simply the forcing function. So f of t is the forcing function or the driving function. So give me any right-hand side of this differential equation, and I can use this integral formula to compute an answer. And what's really compelling about that is I could swap in and out multiple functions and just test the system's behavior to those functions. But there's really something more telling that's going on here. And that's what I want to address right now with something called the impulse response. So the impulse response, the notation that's commonly used is the Greek letter xc, so xc of t. It is a solution to the same differential equation that we just solved. So I'm going to solve the same differential equation, but I'm going to use the xc variable because I'm doing an impulse response. Equal to, and instead of forcing with f of t, I'm going to force with delta t. Now, what this results in, and these are still going to be rest conditions, so it's xc of 0 equals 0, x prime of 0 equals 0 as well. And the idea here is, because we're at rest initial conditions, it's going to look exactly the way that this problem looked previously. It's just the Laplace transform of f of t, capital F of s, since it's the delta function, that'll be 1. And so what you'll end up with is capital X of s equals 1 over s squared plus 6s plus 8, which is the same thing as saying that the inverse transform of this xc of t is just this function that we have in parentheses here. It's minus 1/2 e to the minus 4t plus 1/2 e to the minus 2t. And if you remember our conversation in class about the sifting property of the delta function, you can see exactly here, if we take our formula that we have down here for y of t would simply be the integral from 0 to t of delta t minus u times minus 1/2 e to the minus 4u plus 1/2 e to the minus 2u du. And the sifting property says that if you have the delta function integral, or if you have the integral of the delta function times any other function, then what happens is whatever value of the variable, in this case the variable is u, that makes the delta function 0, that gets evaluated at the other points. So for instance here you can see that when u is equal to t, this is 0, so all of the u's in this function will be evaluated at t, and we'll just end up getting this piece that we got before. So you can see that when f of t is the delta function, you simply get this piece here, and this piece is called the impulse response. So what is the importance of the impulse response? Well, the idea is that essentially what you have, when you go back over here and look at how we constructed this problem, in the case where you had s squared plus 6s plus 8 y of s equal f of s, this is really just the idea that you have the delta function on the right hand side, and the one that was on top here is simply the delta function's convolution with that. So in other words, if this is xc of t, the unit impulse or the impulse response, then what this formula is suggesting is that if I wanted to find y of t, all I have to do is take the integral from 0 to t of f of t minus u times xc of u du. So that the idea is our function y of t, that's the solution to this differential equation, is nothing more than the function f of t, the forcing function, convolved with this impulse response. So that is a very important formula. If I can find the impulse response for a given differential equation, then the solution of that differential equation is simply the impulse response convolved with the forcing function. And that's an incredibly important result known as Duhamel's principle, and that's talked about in another video. I want to take this a step further. Like we've shown how to find the impulse response. It's simply to take the same differential equation and make your forcing term the delta function and then solve it the way you normally would, and that's called the impulse response. I want to talk about the unit step response. So let me create a little bit of space here. See if I can delete all of this in here. Try not to delete everything. All right, so let's take a look at what is called the unit step response. So the unit step response is very similar to the impulse response. It is u double prime plus 6u prime plus 8u. So I'm looking at that original differential equation. And instead of putting the delta function on the right-hand side, you put the heaviside function, which is called the unit step function. So I'm going to put the heaviside function, or the unit step function, on the right-hand side and solve the differential equation. Again, we are keeping rest initial conditions. You can do these problems at conditions other than rest, but it makes it a little bit more complex to determine what's going on. So if I take the Laplace transform of both sides, because the rest initial conditions, we're just going to get the characteristic polynomial times the transform variable, which I'll call the transform variable capital U of S. And on the right-hand side, I take the Laplace transform of the heaviside function. We know that that is 1 over S. So if I solve for the transform variable, I get 1 over S times S squared plus 6S plus 8. Now, what I want you to recognize is that this is simply a convolution happening. In other words, if I take the inverse transform of this side, we know that that would be u of t, which we call u of t the unit step response. And over here on the right-hand side, we have a convolution of an inverse transform of something of the form 1 over s convolved with 1 over s squared plus 6s plus 8. Now, remind me, what is the inverse transform of 1 over s squared plus 6s plus 8? Well, we had it right here. It is the unit step, or it is the impulse response. So this term is xc of t, the impulse response, and the inverse transform of 1 over s from earlier in the semester was 1. So we know that the unit step response is simply a convolution of the impulse response with 1. But if I think about that and the convolution integral here would be the integral from 0 to t of xc of u du. Because you would just, 1 would be at t minus u, but it's just 1. It's just a constant. So this is the solution. This is the unit step response. It's the integral of the impulse response. More appropriately, they have this relationship. If u of t is equal to the integral from 0 to t of the impulse response, then using the fundamental theorem of calculus, that would suggest that the derivative of the unit step response is the impulse response. And that is the relationship that they have. Meaning, if you solve for the unit step response, you can find the impulse response simply by taking the derivative of your solution. And vice versa, if you find the impulse response, you can find the unit step response by integrating your solution. They are a derivative integral sort of pair, right? They're paired through either the derivative or integral, depending on how you want to look at it. And both of these are the key to expressing solutions of differential equations that have arbitrary right-hand sides. So going back to what we discovered over here, kind of tying a neat bow on the semester, if you will, this says the behavior of a system under forcing is essentially a convolution of impulses with magnitude f of t for every t. Meaning that your system is starting from rest, because you have rest initial conditions, and if there were no outside force, in other words, if there were no forcing function, the system starting at rest would just stay at rest. You would get no motion in the system whatsoever. But the forcing function causes there to be motion. What kind of motion does the forcing function cause? Well, the forcing function causes a motion to occur, which is essentially a series of small kicks or small impulses that have size equal to the function at each point. And the solution behavior that we observe is a convolution, which is a matching and pairing of every system response at every point in time from then on caused by that impulse response. If you ever take a signals and systems class, you really see this a lot better as sort of a continuous changing sum of additions of impulse responses over time gives you the solution to the differential equation over time. It's sort of a difficult thing to wrap your head around maybe, but it's a really nice theoretical result in that we can simply find solutions to differential equations by looking at convolutions of an impulse response with our forcing function. All right, thank you for watching.